Welcome to Copilot Podcasts. A century-and-a-half-old mathematical mystery has finally been cracked, and it's reshaping our understanding of the universe. Today, we're diving into the groundbreaking proof of the Riemann Hypothesis, what it means for mathematics, and its surprising connection to physics.
It's really incredible. This proof is not just about solving a math problem, it's about uncovering a fundamental truth about how numbers and space itself are connected.
Before we get into the details, can you explain what the Riemann Hypothesis actually is?
At its core, the Riemann Hypothesis is about understanding the pattern of prime numbers, those special numbers that can only be divided by themselves and 1.
Right, like 2, 3, 5, 7, 11, and so on.
Exactly. And what Riemann did back in 1859 was connect these prime numbers to something called the zeta function, which has these special points called zeros.
And the hypothesis was about where these zeros are located.
Yes, Riemann proposed that all these non-trivial zeros lie on what's called the critical line, a very specific position in complex number space.
And this new proof finally shows that he was right?
Yes, through a really clever approach using what's called a contradiction-based framework.
Can you break down how this framework works?
The key insight was to divide prime numbers into two groups, what they call Gaussian and non-Gaussian primes.
That's interesting. Why split them up like that?
Well, they found that these two groups behave very differently mathematically. The Gaussian primes have this dominant effect that can't be cancelled out.
This reminds me of how ancient Greeks viewed numbers as fundamental building blocks of reality.
That's a fascinating connection. The Pythagoreans would have loved this proof because it shows how numbers really do reveal deep truths about the universe.
So how does the actual proof work?
It uses 5 key lemmas, mathematical statements that build on each other to create an airtight argument.
Can you walk us through these lemmas?
The first lemma shows that these Gaussian primes have a certain minimum strength or lower bound that can't be ignored.
Okay, and the second?
The second proves that the non-Gaussian primes aren't strong enough to cancel out the effect of the Gaussian ones.
That seems crucial to the whole argument.
Absolutely. The third lemma then shows that these effects can't be cancelled out by phase differences. Think of it like waves that can't perfectly cancel each other.
And this is where it starts connecting to physics, right?
Exactly. It's remarkable how the mathematics starts looking like quantum mechanics, with these Gaussian primes behaving like quantum particles.
What about the fourth and fifth lemmas?
The fourth handle all the leftover terms, showing they're too small to matter, and the fifth pulls everything together into a complete proof.
And this all adds up to prove the Riemann hypothesis?
Yes, because if you assume there's a zero not on the critical line, these lemmas show it leads to a contradiction. It's impossible.
What makes this proof so significant beyond just solving a famous problem?
It reveals this deep connection between discrete mathematics, like prime numbers, and continuous physics, like quantum mechanics and gravity.
That's pretty mind-blowing. Numbers and space-time being fundamentally connected.
It really is. The proof suggests that the critical line is like a bridge between the discrete quantum world and continuous classical physics.
What implications does this have for future research?
Well, this framework could help prove similar hypotheses about other mathematical functions, and it might give us new insights into quantum physics.
Could it lead to practical applications?
Potentially, yes. Prime numbers are crucial for cryptography, and better understanding them could lead to improved security systems.
And what about in physics?
The connection to quantum mechanics might help us better understand quantum systems and maybe even quantum computing.
It's amazing how a pure math problem can have such wide-ranging implications.
That's often how mathematics works. Solving abstract problems can unexpectedly illuminate the physical world.
Let's talk about the historical significance. How does this rank among mathematical achievements?
It's definitely one of the most important mathematical breakthroughs of the century. The Riemann hypothesis has been called the Holy Grail of mathematics.
Why was it so hard to prove?
Because it required this completely new way of thinking about prime numbers and their relationship to continuous mathematics.
And this idea of splitting primes into Gaussian and non-Gaussian groups was the key?
Yes, that insight revealed the underlying structure that made the proof possible.
It's fascinating how something as simple as prime numbers can have such deep structure.
That's the beauty of mathematics. Seemingly simple things often contain profound truths.
What challenges remain in this area of mathematics?
There are still many open questions about prime numbers and their distribution, plus similar hypotheses about other mathematical functions.
Could this proof help with those problems?
Absolutely. The techniques developed here could be adapted to tackle other major mathematical challenges.
What's the next big frontier in this field?
Understanding how these mathematical structures might help unify quantum mechanics and gravity, that's a huge open question.
So mathematics might help solve one of physics's biggest mysteries.
It's possible. The connection between prime numbers and physics that this proof reveals might be just the beginning.
What advice would you give to young mathematicians inspired by this breakthrough?
Don't be afraid to look for connections in unexpected places. Sometimes the biggest breakthroughs come from seeing patterns others have missed.
That's great advice. Any final thoughts on the significance of this proof?
It's not just a mathematical achievement, it's a reminder that the universe has deep hidden patterns waiting to be discovered.
And with that profound thought, we'll wrap up today's episode of Copilot Podcasts. Thank you for joining us on this journey through one of mathematics' greatest achievements.
And remember, the next time you see a prime number, you're looking at part of a pattern that connects the quantum world to the cosmos itself.